Jambo, Hotep, Nangaret, Kumarikorpo. Hello, guys. I am Dr. Marcelini Dabo, an African from Senegal. So I am a consultant engineer in industry, an independent researcher, and today I will be talking about first order ordinary differential equations in the sense of the theorem that I have edited uh, for the application of identification in dynamical systems. Okay. So if you have been following this channel, what I want to tell you is that I have been talking about first order and second order systems. For the first order systems, I have talked about their responses in terms of laws for autonomous systems and also for initial responses, both for second order systems and first order systems. So, talking about these systems, I choose only to use the approach with time. I don't most of the time talk about the transfer functions, only if it is for comparative study between the temporal approach and also the frequential approach. Okay. So for the first order systems and both of them, first order and second order systems, I have chosen to talk about only the approach by time. Use and study also stable systems. That are the two conditions, that are the two um, conditions or the two choices that I have made to do these studies and present the things to you. Okay. So during the previous studies, what I have done is to present the results, the laws that are um, the response of the systems for autonomous system, and also the response, an initial response for a first order system. And then after presenting that, what I have done is talk about what I have called ISO time constants. Okay. These are formulas based on the time response in order to compute the time constant of a first order system at any given position of the output on the transient response. Okay. It is possible to do it, but it is also possible to do it uh, uh, considering the rise time of the dynamical system. Okay, so there is a rise time, there is also a time constant. There is also a time response. Okay, rise time is defined between two percentages of the equilibrium that are fixed. It can be for the autonomous systems, the equilibrium can be the zero, and for the initial response, the equilibrium is a static gain multiplied by the amplitude of the input. The third thing is the criteria that I have introduced to do identification of systems, particularly for first order dynamical system. This is what I will be presenting to you in this presentation as my first theorem. So I have talked about this in a previous video that I will be able to share with you the reference. And then for the last first order dynamical system, I talked also about the design of the dynamical systems in terms of temporal performances that are the time responses between different percentages and also the time responses at a given fixed percentages of the equilibrium. Might it be zero or it be the final value in terms of initial response. For second order systems, what I want to remind you is that I have introduced a very important innovation in science and techniques, particularly in control systems, is that for any given second order dynamical system, there is only one time constant. That is a double of the relative time constant, a concept that I have introduced. And that value is equal to 1 divided by the product of the damping ratio by the natural pulsation. So this for second order systems. And having this in mind, considering that for any given dynamical system, moving from one point to another, it is achieved by after a time response that is equal to a multiple of the time constant of our considered system. Might it be a second order or first order? Okay. So now if you are ready, we can go now for the presentation that I will do for you. So if you want to contact me, here is my email. You will be able to contact me here, contact at daboacademy.com. Okay. All right. So let's go. So I have talked to you about this book. This is a French version, but the English version will be coming soon also. So be ready. It will be here. It will be available in the few, probably the end of year and also the beginning of next year. Okay, this is what I can tell you. So let's now consider a first order dynamical system here, as you have it as a dynamical ordinary differential equation, where you have normally the A0 will multiply this S of t. S of t is the output. The derivative, first derivative according to time is written like this one. Here is the entrance, the excitation signal. And then dividing by A0, that is different from 0, you have here the time constant, okay, and here's the static gain. Why static gain? Because when you have small variation, these terms will vanish, and then you will have just the output that is equal to a constant times the input. And then when we do this, we see that to check the solutions, we don't need a Laplace transform to go and find the solutions through the Laplace tables, the Laplace transform tables. We don't need it here. What we do, we go directly from this equation to the solution when the system is an autonomous system, meaning that when here you have the output that is equal to this expression, and the autonomous system means that the input is equal to 0. So you have all this expression on the left part of the equal sign that is equal to 0. And to have a response, you should move the initial condition from 0 and to put it in a place that is different from 0. And then if the system is stable, what is our hypothesis of the beginning? It's our assumption also. We just suppose that we go, when we release our system, it moves to the equilibrium with this time constant, okay? If you consider an initial response, the expression of that is given here with the exponential here, that is exactly this one, because you have minus td, so the minus t enters here, and then you have td minus t divided by the inverse of tau here, as you can see, and then this inverse is exactly what you have here, okay? The initial condition is here, so when you give the global expression of this, you have the amplitude of the input, that is a step, okay? And then here, the day over A0 is a static gain. So the equilibrium point is the product between static gain and the amplitude of the step response, of the step, okay, input. So if the initial condition is equal to 0, what you have 1 minus this expression times the exponential. And then, no, if it is 0, you don't have 1 here. If it is 0, you just have the equilibrium that will factorize by 1 minus the exponential, that is the expression that you have here. This is a more known expression in control systems because when people use the transfer function, they suppose that the initial condition is 0. Transfer function, just a comment, is limited, of course, because it considers initial conditions equal to 0. If you consider that for this dynamical system of first order, what you will be having for as an answer for this one, the S of t, is that you will not have a dynamic here. So an autonomous response is not possible to be seen going through a transfer function because your initial condition is 0. And therefore, if your system is stable, as we make our assumption, your S of t will just stay flat, meaning at equal to 0 all the time during. Okay? So this at the left is a response of an autonomous system, and this at the right is a response of the first order initial response dynamical system. Okay? So now from here, let me show you that for the autonomous system, what we do, we define an output as we have seen it like this, and then we define a percentage that we can reach of the output according to the initial condition. For example, if you position yourself here, you are at 37% of the initial condition. Okay? If you come here, you may be at 90% or things like that. Okay? So consider now that we apply to this gamma a Neperian logarithm, and then this will yield to this result if you check it very well. So you will have the time response at a given position here is equal to Td minus tau log Neperian logarithm of the gamma I, which is S of the corresponding position of time divided by Sd, that is the initial condition of the output. Okay? Just consider the example of an RC serial circuit. Okay. And then if you consider that example, you will see that when you charge the capacitor through the resistor that you have for a given time, you will have an initial condition of voltage at the capacitor. And then from there, if you remove if you remove the generator and close the RC circuit, serial RC circuit on itself, you will be having a decay of the voltage through the resistance that will have this dynamic. So now for the initial response, you will take this expression, and through this expression also what you do, you write it like this one, like an autonomous system. You can see that it is an autonomous system, a relative autonomous system according to the equilibrium, in fact. Because the S of t, you will remove from it the equilibrium. The Sd, you remove also the equilibrium. And the expression of the exponential that you have here is the same. Okay? So from this expression, we define the gamma according to the equilibrium function of Ti, and then this is equal to S equilibrium divided by Sd of the equilibrium, related to the equilibrium, meaning that Sd, every one of them, you just remove the equilibrium. And then if you want, for example, a time response at a given percentage here, this percentage that is here, you will be using this formula to compute it, okay, for an initial response. Very important to know, okay? So, but if your initial condition is equal to 0, so now this expression will become the gamma equivalent. It is equal to 1 minus the output divided by the equilibrium directly, and then you will be considering the complement at 100% of this percentage. Okay, for example, if here you have the output that you consider here, you divide it by the equilibrium, you will have this expression that is equal to around 37%. And then if you take the complement at 1, at 100%, it will be equal to 63%. That is a famous result known on control systems. Don't forget that I call this expression isotime constant, because even here, from this, at any given point, position of your transient response here, for your autonomous system, you will be having Ti minus Td equal minus tau log of gamma E. But if you need to compute the tau, you derive the tau, you just decide to fix your gamma I, wherever you want it. If you fix it, for example, here, you make a projection, you have tau, Ti here, you remove the Td, that is a translation that you can do here, and yes, then you divide by ln of gamma I, where gamma I is this value of output that you can read here on the vertical axis, divided by this initial condition that you have here, and then apply the Neperian logarithm to it. And therefore, if you divide to all this to the opposite of this whole expression, you have directly your tau. And this is true for any given point that you will be choosing on the transient response here. Very important to understand. We can do the same thing with the rise time between 2 points that can be chosen here on this axis, where you have Tj minus Ti, and then for this to compute the tau, you can fix any given different points here, such that the Ti is less than Tj, and then you divide by the opposite of their corresponding logarithm. You divide by the opposite of the difference of their corresponding logarithm of the percentages. So again, the gamma that you have here, okay, will be considered as this gamma for an autonomous system, or this gamma for a initial response. Okay, so now once I define this expression of time, okay, the ISO time constant formula according to the rise time, what shall I be doing? I just have to do, I just have to consider that the Ti that I have here, okay, the Ti that I have here, I can translate this one and then have Ti minus Td, and then this is equal to minus tau logarithm of gamma I. But if in my process I consider a different time Tj such that I can position a Tj here that is greater than Ti, I will have in this formula Tj that is equal to Td minus tau logarithm of gamma I. And then by dividing the two times, meaning that by dividing the Ti minus Td by Tj minus Td, you can see that the minus taus will be simplified, and I will have the ratio of constants that is here. Okay? And then doing the ratio of the constants, I will have also a constant. So what does it mean? It means that if you take the relative time according to the starting time, you will be having if you consider them at a given point such that the output corresponds to a given percentage, for example, 90%, 10% as the rise time. If you do the ratio, that ratio should be equal to a constant that is logarithm of 90% divided by logarithm of 10%. So this is the fundament of the theorem that I have established, that I have announced, and this is what I am currently showing to you. Very important. So I call it Dr. Dabo's first theorem. Here, Theo and Rema. Theo is God. Theophil is a guy who loves God. Rema is a creation. Okay, so Theorema, the creation of words of God. Okay, you have logos also that is different from Rema. So this theorem I have established is to do system identification. Let's consider that you have done data acquisition from a dynamical system, whatever it can be. You can consider a RC system, a RLC system, a motor that you, for example, you run it with a step, and at a given time you stop it, and then you let the motor goes down. Okay, the speed of the rotating motor goes down without any brake, without anything, but it goes down naturally. So if you take the data that you have registered, if you consider the ratio between the time responses, for example, at 90% of the initial condition, that is 95% of the initial condition, 5% of the initial condition, you do the ratio between the two points of time. If that value is equal to this one, that is, let me show you, that is here, okay, 0.0 171, okay, 171, you are sure that what you have as a dynamic is a first order system. You can also, in the case of always another considered percentages, you combined using 90% and also 10%. If you use these two percentages, if you compute the ratio of their time responses from the smaller to the bigger one, you are supposed to have this value. Okay? So I was saying if you go from this one and this one, you have this response. Okay? And then if you also go from the last one, you consider just that you go from 80%, you consider 80%, and then you consider 20%, you will be able, if you do the ratio of their time responses from the smaller to the bigger, the response that you should have for a first order system, if you have a response equal to this value, therefore you are in front of a dynamical system of first order. Sorry, I just noticed that it is written in French because I do videos in French and in English, and I didn't change this. So don't worry. It is just written. Everything that is written is what I am currently saying. Okay. So I have defined this ratio here, as you can see. Okay, so the ratio is defined here. As I was telling you and explaining you is that if you consider this ratio, what you have is the time, you do the ratio of the times from the smallest to the bigger time, and then you will get a constant. And then if you do it, if a constant, if the ratio between 95% of the initial condition, 5% of the initial condition is equal to this, you are in front of a first order dynamical system. And you can do it also. You can choose this ratio, these two percentages, excuse me, or the combination of these ones. Okay. Notice that if you take a data, okay, coming from your given acquisition, and you want to identify which system is behind, what you do, you fix the values of the given times, and then you compute the ratio corresponding to these percentages where you locate the times. Okay. And then if it is equal to this one, it is enough. Your system is a first order system. If you position the times at a given corresponding percentage of the initial condition that are respectively 90% and 10%, you do your ratio computation. If it is equal to this one also, be sure that you have a first order system. Or same remark for this one. Okay? So now in the case where you have first order, in the case where you have an initial response, okay, if you consider an initial response, and then for that initial response, you have an initial condition that is equal to 0. So you consider the same philosophy by considering the percentages of the equilibrium of this, okay? And then, the complement that you have here to 100% will be 100 minus 95, and then you will be considering 5% here. And here the complement will be 100 minus 5, and then you will have 95. So same for the others. And then well, you will be going from 5%, okay, to 95%, as you can see the complements here. Okay. So now I was just changing the ears. Okay, so here, what you have, the headsets, what you have here is this expression, and then this will confirm that you have a dynamical system of second order. If the initial condition is not equal to 0, the percentage will be kept like this one, and then for the initial response, you will compute it, the percentage like this one. Why I am giving you this? Because sometimes you can have, for example, a NERC circuit, okay? And then you do a first excitation of step. You go from 0 volt to 1 volt, and then you see the response of your system. After that, you go from 2 to 5. You check the response. After that, you can go from 5 to 2.5, for example, volt. And then you check the response of your system in terms of the voltage, the capacitor voltage. Okay. And then if you do so, if you position yourself to compute the time response at a different point, that is the initial condition of 0. For example, if you consider going from 5 to 2.5 volts, so you will be having something that is not easy to compute with the more known formulas, because you will be going from 5 to 2.5, so your initial condition is not equal to 0, and other stuff like that. Okay, so to have the percentages at which you can compute, you should use this formula, meaning that if S of t is equal to 95% of 5, okay, so you will be having kind of 4.5 volt, for example, or 90. Let's just take, to simplify computation, we take 90% of 5, so it is 4.5 volt. You put 4.5 volt here, minus the equilibrium, that is 2.5 here. You divide by 5 minus 2.5. That will be giving you the corresponding percentage where you are, okay, upon your system, okay. And then you will be position yourself there at the given value here, and then you read the corresponding time. You do the same for the second point, and then you read the corresponding time. You do the ratio from the smallest time to the biggest time, and then you will, if you have this value, therefore you are in front of a first order, or this one for the corresponding percentage, or this one, 0.14 for the corresponding percentage. This is what I can tell you. So this is a theorem that I have announced, okay, for the first time in control systems. Okay, and it will help you to do identification of dynamical systems of first order. So please notice it very well. And then if you have questions, I mean, you can contact me. Okay, I will be happy to answer. So if you want more details about what I'm saying, I invite you to check this video, okay, on my YouTube channel. Please check this video where you will be able to see all the details. Sorry for this video because the English version is not yet done. Yes, I have forgotten. This is in French, but I guess even if you move for the first part, I will give in this video, I just present the basis of the dynamical, the responses of the systems of first order. Might they be autonomous or initial response? And then in the second part of the video, I take some examples, I share some examples in order to let you see how I compute the time response and how I do identification also, because the principles I use is I just go from what? I go from a given randomized generated time constant. So I generate a randomized time constant, and then I do the simulation as I know, in fact, that even if I know in fact that I am doing simulation of a first order system. Of course, if I verify the theorem, I am supposed to have the good results. Okay, I'm talking about this theorem. Okay, so and then from there I will be able to derive, of course, the time constant, to derive the static gain, and the identification of my system will be very clear. So again, you will be able to check this video if you are if you can understand a bit French and understand the essential ideas. I hope so. Again, sorry for this reference. Uh, I don't yet prepare this video in English. So don't forget, this is a book that is coming very soon in French, probably end of the year or the beginning of next year. So I hope you have enjoyed this video. Please subscribe to my channel, like and share with your people, because I think that this can be helpful for different people. And don't forget, do and try to achieve your dream about the things that you are called to do. I am very happy. I am thankful to God because my part, I guess, I have tried to do something and it is very rejoiceful. So again, thank you for watching. And then please, if you have any contact, if you have any question, uh, if you want to discuss this subject, please, you just can contact me. My contact is here. Okay, please contact me to this through this email. So again, thank you, and then I hope we will be able to you will be able to see again other videos very soon. Bye.